In this video, we're going to look at how to write a scalar surface integral when the surface that we have is already written explicitly. So let's suppose by that we mean that it's been defined as z equals some function of x and y. So we're just continuing this idea of scalar surface integrals. And let's suppose that we have a function given as z equals f of xy. Well, we can parameterize it as follows. We can write a vector function where x and y remain our parameters, and our first component can just be x. Our second component can be y, and here you can see that we can define z as a function of x and y, so our third component is just whatever that surface is in terms of x and y if it's been given to us explicitly. Okay, so remember that if we want to calculate scalar surface integrals, we need the following. So this is an integral over the surface where we might have some kind of mass density function, and we write that the double integral over the surface of our density function f of x, y, z times this surface area element is equal to the double integral over the parameter region of f of r of uv, and we multiply by the magnitude of the cross product of partial derivatives of r with respect to each of the parameters times dA. Could be du dv, dv du. Right? This is what we're working towards, but now we're thinking, what if our function is given to us explicitly? Well, we do the same thing, but we might be able to come up with a formula that we can apply any time that our function has been given to us explicitly. So let's see how we might do that. Let's take our parametrized vector function that represents our surface, and we're going to find this quantity. So that means we need the partial of the vector function with respect to x. Let's find that vector. And then we'll need it with respect to y. Those are our parameters. So with respect to x, we'll have, well, partial of x with respect to x is 1. Partial of y with respect to x is 0. And partial of z, or f of xy, with respect to x, I'm just going to write that as z with a little subscript of x, the partial of z, which is f of xy. Let's do the same for the partial of our vector function parametrized surface with respect to y. So the partial of x with respect to y will be 0. Partial of y with respect to y is 1. And partial of the function f of xy, or z with respect to y, we'll write it as z with a subscript of y. Now let's go ahead and find the cross product of the partial with respect to x crossed with the partial with respect to y. And then we'll find its magnitude, and hopefully we can come up with a formula to evaluate scalar surface integrals for explicitly defined functions. So here we have ijk, and our cross product is going to be, well, we have 1, 0, partial of z with respect to x, 0, 1, partial of z with respect to y, and this is going to give us I. That's going to be a negative partial of z with respect to x, minus j, and that's going to give us a positive partial of z with respect to y, plus k, and that's going to be a 1. So we have this normal vector is negative partial of z with respect to x, partial of z with respect to y, and 1. And to find the magnitude, which is what we really want, of partial with respect to x of our parametrized surface and partial with respect to y, we'll take the square root of negative partial of z with respect to x, which is just going to be partial of z with respect to x squared, partial of z with respect to y squared, plus 1 squared. And so there it is. We're almost there. We have our area element, and so we're able to write for any explicitly defined surface. The scalar surface integral is going to look as follows. We're integrating over the surface some kind of mass density function, or maybe temperature, and we have a area element for the surface. And this is going to be, we integrate over our parameter region with respect to our parameters, our function f of x, y, z, or you could call it f of x, y, whatever, either way. And then we're multiplying by the square root of partial of z with respect to x squared plus partial of z with respect to y squared plus 1 dx dy or dy dx, whatever this may be. We'll call that a dA. And that is a scalar surface integral for an explicitly defined surface.